Today's talk is about my experience that I gathered during implementing the physical units library for C++ that's intended to be standardized as the part of the standard library. We were hoping for C++ 23, but maybe because of this COVID situation right now, we'll have to target C++ 26. We'll see how it works. But anyway, the subject of metaprogramming still evolves, and I would like to show you what is the current situation and the future. The plan for today is that we'll be talking about the user experience, why user experience is especially important for the library I write, and what we can do to improve the user experience with templates. After that, we'll scope on new toys in the toolbox that we got with C++ 20. We'll talk about the future, what are the possibility to extend the templates subject in the language, and about some proposals that are already submitted. And at the end, we'll scope on the performance, because it's the most interesting subject in C++, right? This is why we are doing this, and this is why C++ exists on the market after 30 years. It's the fastest language in the world. So, user experience. In my physical units library, sorry, I have some technical issues with the code. It worked maybe a second before. Give me a moment. Yeah, it should work now. So, yeah, what's the physical units library? Physical units library is basically the library that does the dimensional analysis and units conversion in compile time. So it's type safe to make any operations. Like you can, for example, divide the length by here a scalar, and you have a scalar. You know this probably from chrono duration, right? And this is also similar to what chrono duration does. So we have hours, you can compare them to seconds, or you can add kilometers and meters and get meters. But in the units library, you can also divide different dimensions, different quantities. You can have quantities of length and time, and you will get a velocity from it. And you can make all of the possible operations on those. You can also multiply the same quantities, and you have the quantity squared. So meter times meter is a squared meter. You can divide the same quantities, and you get a scalar. Or you can divide a scalar by a quantity, and you get another quantity. Like something divided by the time is a frequency, like in this case. And to talk about the user experience, let's scope on the really simple example. We will try to implement a function that basically calculates average speed that is measured over some length, some distance, and for some time duration. And of course, the operation is simple here, and it should return speed. So how we want to use it is basically that we are providing 220 kilometers and 2 hours here, and we get the speed in kilometers per hour. But if we pass things like miles and 2 hours, we would like to have the speed in miles per hour, because this is the unit that basically user decided to choose for his operations. Of course, we care about the compile time safety. So if everything is wrong, it should just not compile. And we should have a pretty nice compilation error saying what is wrong. We should have support for multiple units and unit prefixes. And there should be no runtime overhead, right? So it should be as fast or even maybe faster than written using doubles. So let's see how we can do this with the products that are on the market right now, with the most important one and the most popular one, which is Boost Units. With Boost Units, you implement this in this way, that you have a quantity of length, quantity of time, and you get a quantity of velocity at the end. And we divide the distance by time. As you can see, thanks to template aliases, because all of those quantity stuff, length, time, and all of the things actually in the library are template aliases, the developer has really nice user experience as a developer to type a code. It's easy to maintain, easy to understand. However, if we make a mistake, right? It should be divide operation here instead of multiply. If we make a mistake here, this is what users see, end user on the screen. So this is a huge type, and notice those 3 dots at the end of the screen. It means that this line didn't finish yet. This is the end of the first line of the log, because this is only the first line of the log, and there are many more lines in this error log. So even though this function is really simple, and we did really stupid simple error, basically it's really hard to understand what the compiler wants to tell us with this error log. So this is GCC, right? GCC provides big error logs. Clang is better because Clang basically tends to provide more user-friendly errors. So let's see how Clang does. In fact, Clang provided a shorter error line here. There are 3 dots everywhere. But do you know what's the error here? Do you know what's the problem? Probably not. So sometimes a shorter error message is not necessarily better. Just to not talk about boost units, let's look at the other library written by Nick Holhouse. It's a really similar one. It has similar interface, again, using aliases. So the developer has a nice user-friendly environment to work with. But if we make the same error in the code, we'll get an error like this one. So this one doesn't fail to compile with the huge error log. Actually, the error log is a really short one. It's static assert. Static assert saying units are not compatible, that some type trait failed. But actually, do you know what's the problem? We know that the units are not compatible, but we don't know what is unit from, we don't know what is unit to. We can reason about them from this simple function because we can find out probably which units are here, but imagine that you have like 10 or 20 lines of calculations in this function. All of them are converting units, and one of those operations fails. And basically, it's really hard to find out what's the current unit based on the function arguments if you have many lines in the code. So static assert is often not the best solution. First of all, static assert will never influence the overall resolution process, right? So if you want to exclude something or make something conditional in the overall resolution, static assert is not for you. In other cases, you can have an error like this one, but still it's not the most user-friendly one because we still don't know what happens here. Clang is a bit better. With Clang, you have information which type trait failed and what was the instantiation there. But again, we are provided a huge type here, and I'm not sure if you know exactly what's the problem here, right? You have all of those ratios, 1, 1, 1, 1, 0, 1, and so on. And it's really hard to find out that basically this is not a velocity, because this is what error should tell you. So in most template metaprogramming, compile time errors are rare. It's really hard to break, for example, std string or std vector in order to not compile during compile time. Or if you do it, you are doing probably something really, really stupid, so the vector or string didn't compile. But for some libraries, and the physical units library is one of those, actually the main reason to create such a library is to generate those errors for the user many times a day. This is what is the main reason to have this library in your toolbox, to make sure that you are writing correct code and the errors you will expect on a daily basis. So in case of the physical units library, we have to rethink the way we are doing template metaprogramming, and this is the subject of this talk. However, user experience is not only about the compilers or compiler errors, it's also about debugging experience. For example, let's come back to the boost units library, to the same function. Right now it's correctly typed with division operation here, and let's make a breakpoint here. When we make a breakpoint and see into the variable list in one of the IDEs, we'll find out that D and T are actually of the same type, which is not true. It is just that the IDE gave up at some point because of the huge type that is there. It wasn't able to print it, so it basically typed something, and it's really misleading because you think that you are providing the same type to this function, which is not true here. If you go to GDB and do the same breakpoint, you will have information that average speed was typed with those, entered with those two types here. But does it help you during debugging to know what's the input, what's the output? Imagine that those types are not types, but some template parameters. So you don't know exactly what was passed here. Then it's really hard to find out what you are dealing with in this breakpoint. If we type something like p-type of type D, we have even longer error because right now all of the defaults are also provided in the type. So to summarize, I would say that developers cannot live without template aliases, right? Probably as you are writing something in your templated code, you are doing a lot of using aliases or type devs. If you're using type devs, just switch to using, they are better. And you don't want to just stop using this, right? Because it will be a nightmare to work with. But those type aliases are quickly lost during the compilation process. A compiler do not remember them and do not print them in the compile errors, or debugger does not print them during debugging session. So as a result, end users get a huge types in error messages. For many years, we tried to introduce so-called strong type devs or opaque type devs, opaque types to the language. Walter Brown provided several papers in proposals on this subject, but none of them were accepted by the committee. So we still lack this nice feature that actually could make a strong type dev from some other type. So instead of the alias, you have a strong type for the same that alias does, but this strong type dev will not vanish during compilation process. It would help here a lot. But we have to think out something else here, right? To find some other solution. So as a solution, we can go to our old friend called inheritance. Here we have a long template instantiation that was a subject for alias in other libraries, right? And instead of doing an alias, we can inherit from it, providing a strong type for it. So imagine that you have like a vector of ints, for example, in your code, and instead of doing an alias called vector int, you are inheriting from vector int. Of course, it will not work in many cases, but for simple types like this dimension in my case, or unit, which are basically tag types without any implementation, without any members, it is fine. And with this, we get strong types that do not vanish during compilation process. And member-on-member functions of the base class basically will still work with this if needed. However, alternatively, what is different to type devs is basically that we don't inherit all of the constructor and assignment operators. Even if we do using on constructors, we may have some problems and we will not get assignment operators from the base class. And also you have, for example, function foo in a base class that returns the base class, like maybe some factorial function. Then it will not automatically switch to your child class that you just introduced when doing this aliasing, this inheritance, right? With strong type devs, it was an option just to, if you're working on ints, and for example, from operator plus int equals int, then if you will make a strong type def on this one, you will get the strong type def equals as a result of the operation from those two operations, from adding two strong types. So it is not a good fit for everything, but for simple types, for like dimension, unit in my case, so basically tag types that do not have really big implementation of constructors, assignment operators, it is fine and works correctly. However, we have a problem here right now. We have a simple equation here, like length divided by time. Length divided by time creates us the instantiation of this derived dimension with length in exponent 1 and time in exponent -1. So this is this base class that was created by the framework. And it's not easy with this division operator here that takes two quantities of length and time to find out what should be the result here. The result from the framework will be just a derived dimension of those two, rather than speed. How to get to speed? So user assigned nice type from the base type. The language works in the upcasting way automatically, right? So it will go from the child class to base class automatically, but will never go from the base class to the child class. So how to form this speed dimension from those classes? To do this, at some point, I invented, let's say, something called Donecasting Facility. At the very beginning, it was just a simple type trait that basically for any type t returned the same type t. And we have a downcast operation that basically checked this type trait and returned type. And then for every dimension, like for speed, this is speed derived from this derived dimension, we said that if you will see downcast trait of this long type in a framework, then just return nicely provided type by the user, so dim speed, right? So every time the framework ends up with this type will be provided automatically through the conversion. And I had to put this template specialization in every place in the library. It was like more code to create those traits than actually to implement the system of SI. And it was bothering me. So I think on CPPCon last year, I spoke with Richard. And after that, we ended up with the solution that basically doesn't force the user, the implementer of the library, to put those specializations everywhere. So to describe this, let's see such a simple inheritance graph. We have a derived dimension, right? And we inherit dim speed from it. This is what we had in the code on previous slides. Just for the slideware needs, let's assume that our this long derived dimension type will be called dim speed base. So something like this. Okay. And how the downcasting right now works in my library is that we introduce two additional helper classes. We have downcast base and downcast child introduced to this hierarchy. Downcast base basically takes the base class as the template argument, and downcast child takes both of them, the user provided name's name and the base class to inherit from. So we have those two, downcast base and downcast child here. Both of them are using CRTP, so curiously recurring template parameter pattern, to provide this type here and this type here, right? If you're looking on the actually those long instantiations, it looks like this one, but basically this is the same. This and this one, this parameter are exactly the same time. There's the same type copied 3 times. So the type that will be created from the framework and the one that user provided. To understand how it works, how it's implemented, let's see into some simple implementation here. At the downcast base, so the one that's the most base class of the hierarchy, basically provides the alias for this base type and introduces a friend function called downcast guide that takes this type as an argument. So this is hidden friend function provided here. The important part of the trick here is that it doesn't introduce any implementation. It's just a declaration. And the type return here is auto, because at this point, we don't know what is the child class provided by the user. So we cannot provide the type here. But then we introduce the downcastable as a concept that basically says that type T is downcastable if it has this downcast base type provided here. And basically type T is derived from downcast base of this base type, right? Because this is the type here. So we have to derive from downcast base of base type in order to be downcastable. And then downcast child, so the type introduced here, implements the function introduced in a base class. it still returns auto here, but provides the implementation saying return target, because at this point we know exactly what the target type is. So with this trick here, we have a function that we can call as a hidden friend of this function, but at this point we don't know the implementation. At this point we know the implementation, but basically we cannot call this function if it was provided for this type, because this will not work at all. It's a hidden friend. So we need those two parts. One of them is providing a point to call this function. Another one is providing the implementation with the data we know in the child class. And the last thing here to show you is how the downcast works. So basically, you have a downcast that takes some type that is downcastable, and it tries to find out if we provided some nice name to it or not. So the implementation looks as follows. If there is a downcast operation provided by the user for this specific type, then we are using this downcast guide function to find out what is the target type being returned. Otherwise, we are just returning t. And this has downcast concept. It just checks if this non-member function, this hidden friend, is implemented correctly, if it's provided for this specific type. I know that it may be a bit complicated, but you can find the code on the slides after the presentation, and you can find it also in my repository. So you can go back to it later on, but I will show you how the results look for the user, because user will not see this code, it will see the results in, for example, a debugger, right? So you have a debugger with the same exact function. In IDE, you have the information. That's a quantity of length and unit kilometer. And we have quantity of time and hour here. So all of the information is preserved. GDV, the same. Length, kilometer, time, hour. P-type, again, really short, nice type to work with. I would say this is one of the key features of the library that we are scoping on the user experience, on making it as easy to use and as easy to understand. And if you would like to try this library, you can find it on my GitHub. And please provide feedback, please provide requirements. We are really looking for the production, maybe experience with this library, because we would like to standardize it as a part of C++ at some point. So the more users we have, the more feedback we get, the better product we will be able to provide. Before maybe we'll go to the next chapter, I would just want to make sure that we know everything, and maybe there are some questions on the chat. Okay, so let's continue then. So new toys in a toolbox. This is next chapter that will be talking about new C++ 20 tools that we got, and we'll start with so-called non-type template parameters. You are probably familiar with tooth ratio, right? It was introduced by Walter Brown and Howard Hinand when the Chrono library was provided in C++11. Ratio is a simple type, actually class template. It has numerator and denominator as a members here, static members, and the values are provided from the template parameters. However, this code is not that simple, because actually there are many conversions done for those to work correctly, because the ratio of, for example, 1 second, so of a half, is the same if you divide 2 by 4 or 3 by 6, right? It's still a half. So they should end up with the same type. And they don't end up in the same type because type is different, right? If you put 1, 2 here, or 2, 4, or 3, 6, you will end up with different type. That's why there is here a type member here that provides those already normalized values here. So if you put 1 and 2, 2 and 4, 3 or 6 here, it doesn't matter. Always 1 and 2 will be provided here, because those will be calculated here with static sign, static GCD, static ABS, and that all of those are class templates too. So static sign can be implemented this way, integral constant. Static ABS can be implemented this way, using static sign again. So you already have static sign here and here being instantiated. Static GCD is another part of instantiations. So basically it instantiates, let's say, recursively here, and also you instantiate static ABS class templates here. So as you can see, to write something simple like ratio of 1 and 2, you have to make a lot of template instantiations in order to make it work. And to work on the ratio, we have dedicated class template interfaces. For example, to multiply a ratio, we have a ratio multiply alias. And this ratio multiply alias is implemented again as a class template that has some additional instantiations of static GCD, and so-called safe multiply that checks if there are no overflows of the integer type. So as you can see, a lot of class template instantiations involved in ratio. So what we can do with this? Actually, you can use concept functions. When we use concept functions, you can say that numerator and denominator here, numerator and denominator here are basically using those concept functions. This is not how it's implemented in the standard library, because it wouldn't work with C++11. It's C++14 implementation, and we don't have too many branches in the standard library implementations, depending on the language version. So probably maintainers do not want to maintain different version for C++11 and different for C++14 that could use those static GCD functions. And with this, we have better code reuse between runtime and compile time, and we have less instantiation of class templates, of course, right? With ratio multiply, it's the same. We can use again std.gcd, a concept function, and implement safe multiply as a concept function too. So you have much less template instantiations, but still ratio is a template instantiation, ratio multiply is a template instantiation here. So it costs us a bit. In C++20, we get so-called non-type template parameters. One of the, not a template parameter, according to new C++20 definition, is either a structural type, or a placeholder auto, or a deduced class template. So basically the class template with CTAT, class template argument deduction. And structural types, so this new definition is either a scalar, L-value reference, or literal class, where all base classes and non-static data members are public and not mutable structural types. It's important to understand how the compiler sees two types as being the same, as being equivalent. For this, a new definition is being introduced called template argument equivalent. And two template instantiations basically refer to the same class if they are template argument equivalent, and those are following arguments: integral types, enumerations, stud null pointer t, floating point, which is new. We couldn't instantiate the class template with floating points before. Pointer types, pointer to members, references, all of this was always in the language, but also arrays, classes, unions. All of those are possible to use for a template instantiation in C++20. So let's try to write a ratio as an NTTP-based class. We are writing a simple ratio that's not a template anymore. It has numerator and denominator. It gets a constructor that basically does all of these calculations in the constructor initializer list using plain context functions here, the same as we used in the second implementation of ratio. Now ratio multiply actually becomes an multiply operator in this class, right? And what's even more interesting here, we can provide additional multiply operators, not only for ratio by ratio, but also value by ratio or ratio by value. And with such case, the code, for example, that works like this with stud ratio. So you have to provide ratio and ratio multiply, ratio 1/3 of the ratio of the yard. With NTTP, looks as follows. You can just divide it, multiply, and it's easier to type. Also notice that this is also a non-typeable parameter. So with in C++20, you can instantiate a template with a string, and it also works fine. So how it affected my code besides such stuff, because actually this is not the implementation I'm using in the physical units library, but this allows it. I'm using a bit different implementation, but the other examples are exactly from my library. First of all, my unit tests simplified a lot. For stud ratio, I had to use ratio multiply to multiply two stuff, then take this type, the inner type from the ratio, this normalized type, and compare it with another normalized type. I couldn't compare just types here with the same because those could be different types even though they mean exactly the same, like this 1, 2, and 2, 4, for example, right? And right now, I just type it like this. Ratio multiplied by ratio equals this. It makes it much easier. Another thing is I wanted to multiply all of the ratios on the exponent lists. So we have an exponent list, a variable list of arguments here. So basically, if there's only one element here, we just provide the ratio of one exponent. If there is a list, we have to multiply this exponent by the rest of the calculation, right? We are doing, let's say, recursion here until the parameter pack is empty. But with NTP, I can use fold expression just to multiply everything at once. So we're taking benefit of built-in operators here and fold expressions to work with NTTP values that behave like a value. And with this, we get really much easier code to write, much easier code to maintain, and much faster code to compile. That is why I may claim that usage of class types as non-type template parameters might be one of the most significant C++ improvements in template metaprogramming during last decade. So I would like to encourage you to try. If a template parameter behaves like a value for your types, for your classes, it probably should be an NTTP. Try and provide the feedback. I'm really curious what will be your outcome from it. Another new tool that we have in our C++20 toolbox are concepts. How do you feel about such a code? This is C-like, right? This is bad. Void pointer basically means everything, right? So we are laughing from C, we are better, we are having strong types. Yes? So how this generic lambda is different from the one above? Of course, one will fail in runtime, another one in compile time, because lambda will not compile correctly if something is wrong. But still, from the user point of view, from the interface point of view, they mean the same. I take everything and I return whatever. Right? The same with function templates. And actually, with function templates, from C++20, you will be able to write so-called generic functions that looks exactly like our lambda. And the same about this type or class template. In all of these cases, I wouldn't say we are much better than just void star in C. And this is something we are always saying that C++ is better, right? We have strong types. I claim that unconstrained template parameters are the void star of C++. And basically, in every place in the interface, when you have a type name or a class without any constraints, and actually the type provided there cannot be everything in the world, but have some requirements, some constraints, you should express them in the interface for the user to know exactly what is dealing with, and for the compiler too. So what are concepts? Class, function, variables, alias templates, and non-template functions may be associated with a constraint. A constraint specifies requirements of the template argument, and namespace of those requirements are called concepts. So concept is a predicate. It returns bool, right? It's a compile time stuff, and it's always a part of the interface of a template. Right now, in the library, we identify 3 categories so far. First of them are predicates. So these are something really simple, saying, for example, like derived from. All those names are ending with prepositions. We have capabilities, like swappable. As you can see, names are ending with able, and whatever. So this one, for example, check if we can make a swap on 2 types, on 2 objects of the same type. You have abstractions, like bidirectional iterator, that provides some requirements from this type in order to work with some specific algorithm. And this is what we know so far. This is mostly gathered from the range v3 and ranges standardization process. And this is our point of the world. This is an old Sicily map of the world as the people at this time were realizing how the world looks like. Do you see what part of world it shows you? Can you maybe recognize some lands here? Let's try to view on this map from another point of view, from another angle. This is the same map upside down. Does it look more familiar right now to you? I believe so, right? So maybe you should also look a bit different on the concepts and on the experience we have with them. Of course, ranges, algorithms was a great work, and we learned a lot from those. But there are also some other use cases where concepts may be useful. For example, let's take our ratio multiply operation that we've seen already many times. This is an alias that takes 2 type names. So can I put a string and stud milli there? What will happen when I put it there, right? Because I can, because the interface doesn't restrict it for doing this. If I do this, I will have a huge compile time error, where only 1 line will be from my source, and all of the other will be from the insights of the implementation of the algorithm we just broke. If we see such a huge error log, we don't know if this is a bug that we introduced to the code, so this is our problem, or maybe this is a bug in the library because it doesn't behave as it should. So should I submit an issue on GitHub or not? I don't know. It promised to take everything. When I pass anything there, it breaks. So how I can make it better? Let's create a concept called ratio and provide isRatio as its implementation. IsRatio here may be a really simple trait based on variable templates. By default, isRatio is false. And we have a partial specialization of isRatio for ratio type called true. I would say that this family of instantiations is named with an uppercase first letter here. And of course, this naming will not fly in the committee, right? However, this is one of the biggest problems I have right now. How to name a type trait, or sorry, a concept that basically matches instantiation of a specific type. So ratio is already taken. Is ratio is a type trait, because this is what we are used to do. So how to name a concept that basically names a family of instantiations of specific class template? If you have a good name for this, if you have a good idea, please let me know or go to the issue on GitHub of my library to provide your guidance there, because we are really stuck here and we don't know what's the best solution for naming those in order for everyone to understand it. So this is the biggest problem, but we find it really, really useful to have those concepts in our library. The one ranges proposal, the document that basically put ranges to the standard paper, said that the experience of the authors and the implementers of the ranges TS is that getting concept definitions and algorithm constraints right is hard. That is why we often hear that we should limit number of concepts, that defining them is hard, and that we cannot change them after they are defined. So let's better refrain from doing this. But I would say, again, because this is what we explored so far, right? The world is bigger, and actually we know it better right now. For example, if we implement something like this, is it easy to prove that it's correct? That's not a problem to implement this and make sure it's written correctly, right? Of course, defining a concept for something like a forward range or whatever is hard, and if you do it wrong, it will kick you in your butt later on, and we cannot change the standard after this concept is defined. But some concepts like those for family of instantiations or similars are really simple to define, and we should do it. And with using those, when you put this ratio here, you know exactly what you want to achieve. So if you put other types here, you have a nice compile time error saying that basically is ratio evaluated to false. And see, everything is in your source file. No errors from the library internals. Or another definition of ratio. It's not an instantiation of the ratio type, it just requires those two members to be there. Again, it's easy to prove correct, right? Using those, you'll get an information that basically the type T doesn't have a num and then as a member because it's melee or string. Sometimes maybe we don't want to name everything, right? We may put type names everywhere and then do the requires clause. So we just use our type traits. But named concepts are really handy in this and many other cases. For example, let's play with in a policeman game, and let's calculate a fine for a speeding, right? So we return the price here. The speed is quantity of dimension speed. Quantity of checks if type T is a quantity, if type D is a dimension, and check if dimension of type T is equivalent to D. Quantity is an instantiation of quantity. Dimension is either a base dimension or derived dimension. Derived dimension is derived from instantiation of derived dimension base, so some base class that all dimensions are derived from to have the strong typing that you've seen. And base dimension is derived from the base dimension. I had to type it by myself. I will tell you why soon. So I couldn't use this generic type right here. And you can still argue that this is just a syntactic sugar over having the requires clause with type traits. But it's not just this. How would you constrain easily a function return type? With Spine or some other practices than concepts? Or how would you constrain the variable obtained by the user from our function? Or how would you constrain the class template parameters easily without concepts? This is possible with Spinner, right? But you have to introduce additional parameter here and basically provide the the primary implementation of the template empty and provide partial specializations for those. But this is hard. This is hard to maintain, hard to understand. This is not the most familiar and most easy way to do it. And probably it will not pass the code review. Last thing about the concepts I would like to share with you, because this is often something that often I see done wrong in the code. What's the difference here? You have a wrapper that takes type T. You have a function foo that have some type U here, and there is an enable if of type T, saying enable this function in the overload resolution only if T is integral. And here the same done with a concept. The difference is that right column works as expected, left one doesn't. Why is that? Because type T is not the parameter of this template function here, it's a parameter of a class template. So at this point, it's fixed. It's not a, let's say, variable type of this template function. In order to do this, to make it work, you have to introduce another parameter. You can assign it by default from this parameter, and then it will work correctly for you. With concepts, there is no possibility to make such an error. It just works, it's easy to use, easy to maintain, easy to understand. There are a lot of benefits of using concepts and constraints in your code, rather than old Spinner techniques. Even you can constrain the function that is not a template here with concept easily, with required clauses. So benefits of using concepts. They clearly state the design intent of the interface of a class function template, right? You see this in the interface. You open cpreference.com or Docxygen documentation, you see exactly what types are expected by this specific implementation. They are embedded in the template signature. So even if you have things like forward declaration or just a definition of the class or function or declaration, you know it. You don't have to look into insights to find out all of those asserts, expects, or whatever, or static asserts there. They simplify and extend Spinner, right? They are much easier than working with enable if. They are much easier than working with void T. You don't have to provide dummy template parameters to provide Spinner for things like class templates or function templates. And you can easily constrain function return types or argument from variables in the user's code. And they also greatly improve error messages. They provide the error on the entrance to the library code rather than the insides of the library code. So you are working with the code you know rather than the insides of someone else's code. The compilation errors are basically provided before instantiating and the implementation of the template function. So it makes it much easier and better for the users. I can only encourage you playing with concepts. They are available I think on all major compilers right now. So go and try them. I had a really good experience with them, and if at some point I forgot about some concept at some point, I had to fix it later on because it turned out that sooner or later I had an issue there. Working with concepts really changes the world and it changes the way you think about template metaprogramming. And maybe we can have even more better view on our land of template metaprogramming. With this, let's go to the next chapter about the future of the language. Templates are parameterized by one or more template parameters, right? And each of them has to be of one of the parameter kinds. We have parameter kind of type, so you can provide a type like integer. We have non-types, like size_t for the array. We have templates, so basically you're able to provide generators to our templates, right? We provide my deleter here is a class template that we provide here as a generator, not as a specific instance of a specific type. These are called templates, right? So let's see a concept called satisfies. Satisfies takes some type trait and calls a value on it. We have now our is ratio that we already have seen several times. And we can create a ratio multiply that basically have satisfies concept used with is ratio, with our type trait that we provided, right? It gets value from it. And based on this, our concept work correctly. However, if we have this alternative implementation using variable templates, it won't compile, right? Because we provide here a type name. So this is a class template that can be provided here. So template parameter kinds work only for class templates right now. And I will show you in the performance section at the end of this talk that it's good to start thinking more about using variable templates in your code. So this is what we have right now. And the code like this or like this will not compile right now. But there's a proposal written by me 2008 that basically asks to provide support for variable templates in the template signature. This is only one of the use cases for this feature. If you have some cool ideas about other use cases for this feature, please let me know so we can put it in the paper to have a better rationale for it. Basically, the committee liked it, but asked for more use cases. I have some ideas, but maybe you have too. If you have nice use case for a variable template being used in a class template or function template, please let me know so we can put it in the paper and make you a co-author of it. Okay? Another interesting feature that I would like to see in the language are so-called universal template parameter kinds. So as we've learned, we have 3 types of parameter kinds. We have types, non-types, and templates. But you cannot write one signature that basically says, I don't care what the type is there. I want it all. I want to make this template work with everything. So for example, class X with template auto, this is the current syntax we are using for this, says that I'm taking any parameter kind here. It can be a value, it can be a type, it can be a template, and I don't care. Or I can have any number of those. What it allows us to do. For example, we can write this instantiation of type trait that basically takes anything here, any class template, or maybe variable template if with other paper will be accepted too. And basically it checks if this instantiation works correctly, if the type is the same. So I can write a template called instantiation of. And then I can write my ratio multiply as instantiation of stud ratio, instantiation of stud ratio, and it just works fine. I don't have to provide any type traits to detect ratio because the concept already will check it and it will take everything and we will not care if the ratio has type parameters or it has non-type template parameters or have some template parameters. It will just verify if it's a ratio. It opens doors for many nice use cases. And again, we have a nice compile time error with all of the source here rather than the library implementation. It would help a lot to have something like this. In fact, there is a paper on the fly by Walter Brown and Bob Stigo that basically saw my presentation and written a paper. It's called the specialization of. I'm not fine with the name. I think it should be called instantiation of, but basically it tries to standardize the current practice only for types. And in my opinion, standardizing this for only types doesn't have sense. After this paper is being accepted, I would write another one about its instantiation of type trait to put in the standard library because it has only sense if it patches everything. There are a lot of classes that takes non-type template parameters, and there will be more because of C++20. So having something called specialization of that takes only types is not a solution. I don't think it should be accepted until this feature is in the language. Another use case for this may be provided here. Let's analyze those functions. This is C-like interface, right? We have a lot of names. All of them are unique names, and all of the arguments are void star, like in C, right? We know better in C++, we have strong types. If you provide strong types, it turns out that actually you don't have to provide different names for it, and we often use overload resolution, function overloading, for the same function name with different strong type arguments, right? This is what we do, this is what we used to, and this is what works for us. However, for classes, for class templates, it doesn't work. This is what we do right now. We have a named coherent derived unit, coherent derived unit, named scale derived unit. All of them are using some parameters, and they are weak. They take a lot of different types here, right? Type name, type name, type name, type name. We just said don't put type name in the code if you have any constraints about the type. So with concepts, you can provide strong types for those types provided here. So this is equivalent to strong types in function overload. But still here we have different names. Why? Because here you have a basic fixed string that's non-type parameter. Here there is no parameter of non-type parameter, so you cannot easily write the primary template for all of those templates. With this feature, you will be able to write this is derived unit. The default implementation is not provided, but it takes anything. And then you can provide implementation of all of those with the same name, with strong, let's say, parameters, with concepts, and the compiler will do the rest. And you're writing in the same way like you were used to. So right now, the implementation looks as follows. Every parameter has a different name, and you have to remember exactly which name to provide to every parameter. But after this feature, you can just put direct unit everywhere, and it will work fine. There are more use cases for this feature in the paper. So if you're interested, go to it's 1985, I think, and see more use cases there. This paper is already in the pipeline, let's say, and probably will be accepted in the language at some point. So with this, let's go to the last point. So performance. So the thing that may be the most important for you because you care about the performance because you do C++, right? For compile time benchmarking, I would recommend you using MetaBench. MetaBench was started by Louis Dion when he started to work on Boost HANA library. Basically, it's a CMake module that simplifies compile time benchmarking. And can be used to benchmark precise parts of the code only, not only all of the translation units. So it's really nice to do some micro benchmarking there for specific parts of the code. Also, there is a website called MetaBench, where you can find comparison of implementations of different MPL algorithms and their performance. How it works, it basically takes the files written in Ruby and CMake wraps them to make, let's say, our non-user experience in build process. So we defined data sets saying this is the target, CMake target, this is the source file. This is the data provided to the source file for measurement. And this is the name of the data set. We have 3 data sets here, and then we create a chart that has a title, subtitle, and data sets created above. A source file, Ruby source file, looks as follows. You include some stuff here that's needed for you to work with, and then you make a loop that basically takes the argument from this range and creates a loop. And if defined meta bench, you provide things that you want to test, else you provide some other code that basically will be treated as the reference performance. So only the difference is important for you. So after generation, this code looks as follows, right? You have test 1 with some 2 ratios or 2 voids, test 2 with 2 ratios or 2 voids, and so on. And you can also put the NTTP ratio and verify its performance. And the tool provides you a nice graph. This is the output from the graph. You have the ratio NTTP here, so you can see that NTTP is really, really fast in this case. This is the regular standard implementation of ratio. And this is the standard implementation of ratio using context functions that actually no implementation does right now because they would have to branch on C++ 11 and 14. But NTTP ratio is still faster for multiply and divide operations here, because this is what was benchmarked here. However, it doesn't mean that basically NTTP is always faster. For example, if you will not look on the whole operation of multiply and divide that takes 42 seconds here, but you will look only on the creation of the ratios, so only the construction of them, you will find out that actually NTTP is the slowest one because it has to instantiate this constructor. But it's only 2 seconds in those 42 seconds, the construction. All of the rest is taken by multiplying and dividing those ratios. So overall, NTP ratios are faster than for me, but for sometimes it can be slower. And it was raised by Hannah on CPP Now 2019, saying that context is slow. For her benchmarks, it took 2 minutes for GCC 9, 40 seconds for Clang, and less than 5 seconds for PHP. So our compilers are a really bad interpreter of our code. And there's a lot of area for improvement. Some time ago, when I was attending Code Dive, I met with Odin Holmes, and he was talking about the Rule of Chiel. Chiel is a student of Odin, was a student, right now he works together with Odin. And he approached the performance of the compilation of templates in a mathematic way, systematic mathematic way. He just make all of the measurements and provided the results. The less expensive operation is just looking up MMOI's type. Then we can add parameters to alias call, adding a parameter to a type, calling an alias, instantiating a class, instantiating a function template, and Svine at the end. Svine is the slowest thing you can do. Aliases are fast, classes a bit slower, function templates even more slower. Knowing this, you can actually look on the type traits we have right now, and we know how they're implemented, and think how we can do this better to be faster. For example, we have conditional. Conditional is implemented in this way in the standard, that it has a primary template that basically returns true here and has partial specialization on false that returns false. So you have 2 class templates here, and they are chosen. Yes. Yeah, I know. And with Alias templates, you can implement this way. So you're using aliases instead of class template instantiations. This takes only one parameter. So it's instantiated only once for true, once for false, and it's all. There are no more instantiations. And the result for it is as follows. If you're using aliases, it's here. If you're using the standard one, it's here. And yes, and this one is when you're not using this helper here, but directly typing some such strange stuff like this in your code. So this alias here also costs. And the same goes for Clang. Which template is missing in the rule of Chiel? Variable templates, right? At this point, when that Chiel made the measurements, probably it was pre C++14 or C++14 was just entering the market, so he didn't measure the variable templates. So let's try by ourselves. We have is same type trait that basically is false type by default. If it's the same template type, then it's true type. And we have a helper is same v that takes a value. We can plan the same using variable templates with variable template specialization that does the same and provide using is same for the type trait. So this one basically is an instantiation of bool constant. And the result is that variable template is the fastest one. So is same v, if you're using is same v, is the fastest one. Stud is same v, so the one that basically is an variable template for this type trait is the slowest one. And the standard type trait and the one from bool constant on our variable template have similar performance. On GCC. On Clang, it's a bit different, but still is same v is much faster than anything else. Just to warn you, there are other implementations. For example, at the same point that I talked about this on CPPCon, because actually I was talking about exactly the same implementation of the same on CPPCon 2019, there was another talk by other author about also implementing is same in a faster or better way. This is the code. I will not go through it right now. You can find it on CPPCon videos. But when I actually measured this on Clang, it turned out that it's at least 2 times slower than the one that's in the library. And on GCC, actually, I thought that the compiler hanged. There's a logarithmic function that makes all of the lines here. So be aware and always measure. And also measure on different compilers because the user experience may be different. The last question is, what about C++ concepts, right? We talked about concepts. What's the performance? What's the cost of them? So let's, for example, measure the typical dispatch. We make a dispatch here with enable if on odd and even values. And you're doing the same with concept here, with requires clause. Also, I added if concepts from C++17 to just verify how it compares to the other solutions. The results I get is that basically concepts and if concepts are exactly the same. And Spine is much slower for GCC and for Clang. So as you can see, concepts are just a compile-time branch like if concepts. And you should not be aware of them. Of course, they cost something, right? Because they do something. If you don't do anything, just put type name, it will be faster, right? But if you basically, they are not that slow as Spine and they are as fast as if concepts that we basically claimed in C++17 that is fast. And we should use it everywhere in the code. The last thing to tell you about the performance, use concepts in the interface that user sees, right? So this is the exponents used in the dimension. So user may provide the wrong type here, and here should be a check. Also here, in some alias. However, if you are going to some details implementation and those types are already checked and you know that you are not making any errors, you can skip those concepts here because you know that you provided a good concept here and user should not use those types by himself. And in this case, we know already that this is a correct type because it was checked here during the construction of this type. So we don't have to put the concept again just to say that those is are of this concept because they were already checked during when this type was instantiated first time. The previous tests were this is static one, but I also checked on my code base at some point. I implemented those 3 versions with no concepts, all the concepts and concepts in the interfaces. You can find that for production code, the difference is not that much. This is code that does nothing, and this is type-safe code. If you are interested in metaprogramming, benchmarking, and performance of different algorithms, please be encouraged to go to the MetaBench site, and you will find a list of all of the algorithms and libraries there compared with each other. Takeaways. Think about end-user experience and not only about your convenience as a developer. Right? Use C++ concepts to express compile time contracts, improve productivity, improve compile time errors. Use non-type template parameters when a template parameter represents a value rather than a type. And optimize compile time performance. MPL is free at runtime, right? But can be really expensive at compile time. And there is more than one way to do it. And always measure on different compilers to verify if your assumptions are okay. Because your mileage may vary. And that's all from me. Do you have any questions? There's not much time. There's only 2 minutes. Sorry.
Yeah, thanks for sharing the experience with the Unix library, the performance analysis of MPL algorithms. It's really great, and it's a really nice topic to research. And we have time for only one question from the audience. So, what's the rationale to use concept auto syntax for constraint parameters return types?
What's the syntax for it?
No. What's the rationale to use? So why should we use concept auto for the return types? Mm-hmm.
So, for example, if I have a huge calculation done by an engineer that has 100 lines, he wants to make sure that he's returning speed from this calculation. So, first of all, it's the also self-check for the implementer of the function to make sure that he didn't mess up with the code. Another point is information for the user. If you see a documentation saying this is function, it returns auto. You don't want what to expect from this function, right? As a user, you don't know what it will return to you on the auto. We can't return a strong type here like int because basically it may be many different speeds. It may be speed in kilometer per hours or miles per hours or meters per second. So we cannot provide a specific type for you, but we can say at least it is a speed quantity, speed dimension. And please be aware of it, and this is how this function works, right? Providing only auto doesn't provide the necessary information for the user. What is the output of this function?
Yeah, makes sense. Thank you.
Mateusz, thank you for taking time to share with us your experience. Evgeny, thank you for your help. And now you can move to the discussion room and continue to discuss this speech.
Sure. If you have any questions, come with us and ask more questions there. Sorry, there was not much time at the end of the talk.
Everything goes
yeah,
okay.
let's jump in Zoom.